So for the third question, we have two separate payment streams. So Brutus is receiving 10x for 10 years. Caesar is receiving $50 for the first year, and then each subsequent payment is going to decrease by x. And then at this interest rate, both the present values are equal. So we need to find x. So this is a relatively simple problem. All we have to do is just to equate the present value of both these payment streams. So as always, let's visualize everything with a diagram. So this timeline is the most useful thing you can ever draw for this course. So what Brutus is receiving is very simple. It's just 10x per year. So this is just a normal annuity immediate. So there's nothing new here. And then for Caesar, he's receiving $50 for the first year. And then each subsequent payment is going to decrease by x. And he's going to receive 10 payments as well. So by time 10, he's receiving 50 minus 9x. So what is the present value of what Caesar is receiving? So this is essentially a chance for you to apply this formula. So this is the increasing annuity formulas, the general formula. So all you have, so P is the first payment, Q is the subsequent changes to each payment. So in our case, P is going to be 50, and then for N it's going to be 10. And then each change is minus x, so we just substitute minus x to Q, and then we arrive at this expression. So now all we have to do is just to equate this with Brutus's present value, and then just to substitute the numbers to find these terms, and then with a bit of rearrangement, you'll find that x is equal to 3.586733056. So this is the answer. So in addition to this method so in addition to using this formula directly, I would also like to show you a different way of thinking about things. So what's special about these annuity questions is that you can always use a different formula to calculate the same thing. And then the more different methods you explore, the deeper your understanding will be. So Caesar's payment is starting off at 50, and then each subsequent payment is going to decrease by x. So you can imagine having a normal annuity immediate of $50 with each subsequent, with this sort of negative annuity that increases starting at time 2, all the way to negative 9x. So Caesar's present value is going to be the sum of both of these annuities. So this normal annuity immediate, and then this reverse negative annuity. So then the present value is going to be equal to 50,810. So that's just the annuity immediate, and then minus x IA9. So there are 9 payments starting from 1 all the way to 9. And then the present value of this term is going to be at time 1, so we need to multiply by v again to bring it back to time 0. So using this term, we can actually solve the same problem. So this bracketed term over here is essentially the same as this term over here. It's the same as this expression. So whichever one you choose, it's based on your preferences. If you like to use this formula, you can always break things up and then use this. If you like applying this formula directly, you can always use this directly, of course. And then you can actually also show that both of these expressions are actually equivalent. So first of all, you see that both of these already have a 5810. So that's obvious enough. So all it remains is to show that this section over here is the same as v times IA9. So IA9v. And we know that it has to be equal, right? Because this is just a different way of writing out the same payment stream. So I'm going to show you algebraically that it is indeed the same. So let's just write out the formula. So v times an annuity due. So recall that 1 plus I times an annuity immediate gives you an annuity due. So multiplying it by v, I get back the annuity immediate. Then minus v to the power of 10i. And then I'm going to minus a v to the power of 10, so this becomes 10. And then plus a v to the power of 10. So I can actually combine this term into here, because A9, that's just an annuity immediate, so the payment is equal to v plus v squared all the way to v9. So if I add a v10, so this part here is A9. If I add a v10, this becomes A10, right? So this becomes a10 minus 10v to the power 10 divided by I. So you can see that VIA9 is exactly equal to this expression here. So there we have it. You find that I've shown you that algebraically both of these expressions are equivalent. So the whole point of this is just to show you that there are different ways of thinking about things. So I encourage you to experiment with more of these different ways of thinking about things so you can apply the formulas a bit more. You can do what I just did right now. You can check whether they're equivalent. So this whole process here is really good exercise for